I continue my discussion of simple harmonic motion dynamics with a discussion of the simple pendulum. Consider a mass M attached to a string of length L, which is free to swing back and forth. Shown in part A of the figure to the right, the mass is shown to have an arc length F with respect to the vertical axis and inclined at an angle theta. It is displaced from its lowest position by this angle. And according to Newton's second law, for the tangential component of gravity parallel to the motion, the net force on the mass is just equal to that gravitational force, the tangential component of the gravitational force, which is equal to minus mg sine theta. And since that's the net force, that's equal to the mass times the acceleration in the tangential direction. So from that we see that the second derivative of position with respect to time, that is the tangential acceleration, is equal to minus g sine theta. Now, if we restrict the pendulum's oscillations to small angles, that is less than 1, then we may use less than 10 degrees, I should say. Then we may use the small angle approximation. Sine theta is approximately equal to theta, where theta is measured in radians. So we write the net force as approximately equal to minus mg theta. And theta, then, we can replace with S over L. So the net force is equal to minus mg S over L. And the angular frequency of the motion is found to be 2 pi f, which is equal to the square root of g over L. In example 15.7, we find the maximum angle of a pendulum. A 300-gram mass on a 30-centimeter long string oscillates as a pendulum. It has a speed of 0.25 meters per second as it passes through the lowest point. What maximum angle does the pendulum reach? And in this example, our model will assume that the angle remains small, in which case the motion is simple harmonic motion. We solve the angular frequency of the pendulum. It's equal to the square root of g over L. And so putting in the numbers, it's equal to 5.72 radians per second. The speed at the lowest point is V max equal to omega times A. So the amplitude is equal to S max, or the maximum arc length, which is equal to V max over omega. And then putting in the numbers is equal to 0.25 meters per second divided by omega, 5.72 radians per second, equal to 0.0437 meters. The maximum angle at the maximum arc length S max is theta max is equal to S max over L, which is equal to 0.146 radians, or 8.3 degrees. Let's assess. Because the maximum angle is less than 10 degrees, our analysis based on the small angle approximation is reasonable. In Quick Check 1512, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2.0 seconds. If the ball is replaced with another ball having twice the mass, the period would be which of the following? Well, the period, it depends on the length of the pendulum and g, and not on the mass. So the period won't be affected if we double the mass, and the answer is still 2.0 seconds. In the next quick check, on planet X, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2.0 seconds. If the pendulum is taken to the moon of planet X, where the free fall acceleration is half as big, the period will be which of the following? The period on planet X will be t sub x equal to 2 pi times the square root of L over g. Then if we go to the moon, where the g is now g over 2, the period on the moon is equal to 2 pi times the square root of 2L over g, or equal to the square root of 2 times the period on planet X, which gives us the square root of 2 times 2, or 2.8 seconds. So let's consider a simple harmonic motion model. In simple harmonic motion, for any system with a restoring force that's linear or can be well approximated as linear, such as the mass on the spring, or a pendulum undergoing small oscillations. The motion is simple harmonic motion around the equilibrium position. Frequency and period are independent of the amplitude. Mathematically, for an approximate position variable u, the equation of motion can be written as the second derivative of u with respect to the time, equal to minus some constant times u, where c is a collection of constants. The angular frequency is omega equal to the square root of c, and the position of velocity are u is equal to a cosine of omega t plus the phase constant, and the velocity in the direction of u is equal to minus the maximum velocity times the sine of omega t plus the phase constant, where the amplitude and the phase constant are determined by the initial conditions. In this model, mechanical energy is conserved. Limitations of the model. The model fails if the restoring force deviates significantly from linear. The physical pendulum. Any solid object that swings back and forth under the influence of gravity can be modeled as a physical pendulum. Here we show an object. It could be a bat or some cylinder, and it's allowed to swing about a pivot point. The gravitational torque for small angles, that is, angle less than 10 degrees, is equal to minus mg L theta. If we plug this into Newton's second law for rotational motion, that is, torque is equal to moment of inertia times the angular acceleration, we find the equation for simple harmonic motion with the angular velocity equal to 2 pi f equal to the square root of mgl over I. In example 15.9, we treat a swinging leg as a pendulum. A student in a biomechanics lab measures the length of his leg from hip to heel to be 0.90 meters. What is the frequency of this pendulum motion of the student's leg? What is the period? We can model a human leg reasonably well as a rod of uniform cross-section, pivoted at one end at the hip to form a physical pendulum. For small angle oscillations, it will undergo simple harmonic motion. The center of mass of a uniform leg is at the midpoint, so we'll call the moment of inertia equal to L/2. So when we solve, we see that the moment of inertia of a rod pivoted about one end is 1/3 ml squared. So we calculate the pendulum frequency as 1/2 pi times the square root of mgl over the moment of inertia. And then putting in 1/3 ml squared for the moment of inertia, we get the expression 1/2 pi is equal to the square root of mg times L/2 divided by ml squared divided by 3, which is equal to 1/2 pi times the square root of 3g/2l. And putting in the numbers, that calculates to 0.64 hertz. The corresponding frequency, a period, is 1 over the frequency, equal to 1.6 seconds. Notice we didn't need to know the mass. Now let's assess. As you walk, your legs do swing as a physical pendulum as you bring them forward. The frequency is fixed by the length of your legs and their distribution of mass. It doesn't depend on amplitude. Consequently, you don't increase your walking speed by taking more rapid steps. Changing the frequency is difficult. You simply take longer strides, changing the amplitude, but not the frequency. In Quick Check 1514, a solid disc and a circular hoop have the same radius and the same mass. Each can swing back and forth as a pendulum from a pivot at one edge. Which has a larger period of the oscillation? The solid disc, the circular hoop, both, or there's not enough information to tell? The hoop has a greater moment of inertia, and the period of oscillation is proportional to the square root of the moment of inertia. So the circular hoop will have the greater period. And that concludes this video.